Brittle fracture damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of brittle fracture. Based on API 571. Brittle fracture is the sudden rapid fracture under stress, residual or applied, where the material exhibits little or no evidence of ductility or plastic deformation. Brittle fracture damage refers to a type of failure in materials, typically metals or ceramics, that occurs suddenly and without significant prior deformation. This process results in a rapid propagation of cracks through the material without plastic deformation, meaning the material does not exhibit ductility or any noticeable elongation before breaking. Characteristics of brittle fracture include the following. Number 1 is rapid or sudden failure. Brittle fractures often occur without warning, leading to catastrophic failure, as the material can withstand loads up to a critical point and then fail almost instantaneously. Number 2 is crack propagation. The fracture typically progresses along specific planes called fracture planes, often following the material's microstructural features. Crack propagation is generally fast, leading to sharp, clean fracture surfaces. Number 3 is appearance of fracture surface. The surfaces created by brittle fractures usually show a glossy or granular texture, with no evidence of deformation such as stretching or bending. The presence of cleavage facets, where the fracture has split along crystallographic planes, is common, particularly in metallic materials. Number 4 is factors influencing brittle fracture. Several factors can contribute to brittle fracture, including material composition, temperature, strain rate, and stress concentration from notches or other geometric discontinuities. Lower temperatures and higher strain rates generally promote brittle behavior in materials that may otherwise exhibit ductility. Number 5 is applications and implications. Understanding brittle fracture is essential in various industrial applications, as it can lead to premature failure in structural components, pipelines, and machinery. Engineers often design to minimize the risk of brittle fracture by using materials with good toughness, avoiding stress concentrators, and ensuring appropriate operating conditions. Number 6 is fracture's toughness and mechanics. The first is fracture toughness, or low toughness. The ability of a material to resist brittle fracture is quantified by its fracture toughness, which is a critical property in the selection of materials for applications where failure could have severe consequences. Materials that are susceptible to brittle fracture usually have low toughness, which means they cannot absorb much energy before failing. The second is fracture mechanics. The analysis of brittle fracture often involves understanding the stress intensity factor, or K, which measures the stress state near the tip of a crack. Once this factor exceeds a critical value, or Kc, the material will fail. In conclusion, brittle fracture damage represents a significant failure mode that engineers and materials scientists must consider, particularly in the design and maintenance of structures that require high reliability and safety. Brittle fracture damage is a critical failure mode in materials that can lead to unexpected and catastrophic structural failures, necessitating careful consideration in engineering and material selection. Affected materials of brittle fracture damage based on API 571. Carbon steels and low-alloy steels are of prime concern, particularly older steels. 400 series SS are also susceptible. Brittle fracture is a failure mechanism that occurs in materials and they are subjected to stress and do not exhibit significant plastic deformation before breaking. The materials typically affected by brittle fracture include: Number 1 is metals, such as the following. Ferritic steels. Low-carbon steels, especially when subjected to low temperatures or high strain rates, can experience brittle fracture. And high-strength steels. These materials can be susceptible to brittle fracture, particularly in welds or heat-affected zones. And then cast irons. Particularly gray cast iron and ductile iron can experience brittle fracture, especially under stress concentrations. Number 2 is ceramics. Many ceramics, such as porcelain, tiles, and bricks, are inherently brittle and can fracture easily under tensile stress. Number 3 is polymers. Some thermosetting plastics, particularly those that are glassy and not rubbery at room temperature, can exhibit brittle fracture. Number 4 is composites. Certain composite materials can be prone to brittle fracture, particularly those with a hard matrix and brittle reinforcing fibers. Number 5 is glasses. Glasses are also considered brittle materials and can fracture without noticeable plastic deformation. Factors such as temperature, loading rate, and the presence of stress concentrators, like notches or cracks, can influence the susceptibility of these materials to brittle fracture. When designing components or structures as well as when performing inspections, it is important to consider these factors to mitigate the risk of brittle fracture. Brittle fracture is a failure mechanism characterized by rapid crack propagation with little to no plastic deformation. Understanding the critical factors that contribute to brittle fracture is essential for materials science and engineering, particularly in applications where materials are subjected to stress and environmental conditions. Critical key factors of brittle fracture include: Number 1 is material properties. The first for material properties to be considered is yield strength and toughness. Brittle materials generally have high yield strengths but low toughness. The material's ability to absorb energy before fracturing is crucial. The second for material properties to be considered is ductile to brittle transition temperature, or DBTT. Some materials exhibit a transition from ductile to brittle behavior at certain temperatures. This is critical for metals. The third for material properties to be considered is microstructure. The grain size, phase distribution, and other microstructural features significantly affect brittleness. The fourth for material properties to be considered is chemical composition. Alloying elements and impurities can influence crack initiation and propagation. Number 2 for the critical key factors of brittle fracture damage mechanisms is stress state. The manner in which loads are applied, tensile, compressive, shear, can determine the likelihood of brittle failure. The first of stress state is stress concentrations. Notches, cracks, or other geometrical discontinuities can create stress concentrations that facilitate crack initiation. The second of stress state is tensile stress. Brittle fracture is more likely to occur under tensile stress rather than compressive stress, as tension can promote crack opening. Number 3 is rate of loading or dynamic loading. Rapid loading may enhance the chances of brittle fracture due to insufficient time for plastic deformation. Number 4 is environmental factors. The environmental factors such as the following. The first is temperature and humidity. Low temperatures can promote brittle behavior in certain materials and can increase the likelihood of brittle fracture, while certain environments, like corrosive conditions, can promote crack growth. The second is corrosive environments. Chemicals can weaken bonds and create stress concentrators, leading to brittle failure, e.g., stress corrosion cracking. The third is hydrogen embrittlement. The presence of hydrogen can severely reduce the ductility of certain metals. Number 5 is stress concentrations, such as the following. The first is notches and flaws. Geometric discontinuities and internal defects act as stress risers that can initiate cracks. The second is surface defects. Imperfections such as scratches, pits, or inclusions on the surface of a material can serve as initiation sites for brittle fractures. Number 6 is microstructural features, such as the following. The first is grain size and shape. Fine-grained materials often exhibit better toughness compared to coarse-grained materials. The orientation and type of grains can also influence fracture behavior. The second is defects and inclusions. Internal flaws, voids, or inclusions can act as stress concentrators leading to the initiation of fractures. Number 7 is crack propagation. The first of crack propagation is crack tip stress intensity. The stress intensity factor, K, at the tip of a crack determines whether a crack will propagate. High values of K can lead to rapid crack growth. The second of crack propagation is fracture toughness. The ability of a material to resist crack propagation is measured by its fracture toughness. Low fracture toughness can lead to sudden brittle failure. Number 8 is crack path. The crystallographic orientation and microstructural features influence how a crack propagates. Number 9 is geometry and design, such as the following. The first is component design. Poor design that does not account for stress distributions can lead to unanticipated brittle failure. Features such as sharp corners or complex geometries can exacerbate stress concentrations. The second is load path. The way loads are applied can also influence stress concentrations and the likelihood of fracture. Number 10 is fatigue and cyclic loading, such as fatigue cracks. Repeated loading can lead to the initiation of cracks that may propagate in a brittle manner, particularly in materials susceptible to fatigue. Number 11 is residual stresses, such as internal stresses. These may arise from manufacturing processes, welding, or thermal treatment, potentially leading to brittle fracture if they exceed the material's limits. Number 12 is loading history. Previous loading cycles and the history of stress states experienced by the material can influence its susceptibility to brittle fracture. Addressing and understanding these factors can be critical in material selection, design, and failure prevention strategies. Ensuring materials are used within their limits and in appropriate environmental conditions can help mitigate the risk of brittle fracture. Affected units or equipment. Brittle fracture is a failure mechanism characterized by a sudden and rapid crack propagation through a material, typically occurring with little or no plastic deformation. It can affect various units and equipment across different industries, particularly those that involve materials susceptible to brittle failure under certain conditions such as low temperatures, stress concentrations, or certain material properties. Here are some commonly affected units or equipment. Number 1 is pressure vessels. These are critical in chemical and petrochemical processes where materials can experience high stress and low temperatures. Number 2 is pipe systems. Piping made of brittle materials or subjected to low temperatures can suffer from brittle fracture, especially at welded joints or where there are stress concentrators. Number 3 is pipelines. Steel pipelines in cold environments or those carrying high-pressure liquids or gases can experience brittle fracture, leading to catastrophic failures and leaks. Number 4 is storage tanks. Tanks used for storing liquefied gases, particularly at cryogenic temperatures, can experience brittle fracture if the materials are not adequately selected. Number 5 is heat exchangers. Components made from brittle materials may fail during thermal cycling or due to stress concentrations from operational factors. Number 6 is structural components. Steel beams, columns, and other structural elements in buildings or bridges may suffer brittle failure, especially in low temperatures or if they are improperly fabricated or treated. Number 7 is rotating equipment. Equipment like pumps, turbines, or compressors where materials are under high stress can be at risk, particularly if made from brittle alloys. Number 8 is transportation equipment. Components of vehicles, particularly those made of cast iron or high-strength low-alloy steels, can be susceptible to brittle fracture. Number 9 is manufactured parts. Items produced by casting, especially those with high carbon content or poor microstructures, can fail in a brittle manner under stress. Number 10 is forgings and machined components. Parts that have complex geometries or sharp corners may be more likely to exhibit brittle fracture. Number 11 is wind turbine blades. Composite materials used in wind turbine blades can also be susceptible to brittle fracture under certain loading conditions. Number 12 is nuclear reactor components. Certain components in nuclear reactors, such as pressure vessel internals or some stainless steels, can be prone to brittle fracture, impacting safety. Preventing brittle fracture involves material selection, proper design to avoid stress risers, maintaining appropriate temperatures, and ensuring proper fabrication processes. Regular inspections and maintenance are also critical to identify potential issues before failure occurs. Appearance or morphology of brittle fracture damage mechanisms. Based on API 571. The first is cracks will typically be straight, non-branching, and largely devoid of any associated plastic deformation, although fine shear lips may be found along the free edge of the fracture, or localized necking around the crack, see Figure 4:12 to Figure 4:15. The second is microscopically, the fracture surface will be composed largely of cleavage, with limited intergranular cracking and very little microvoid coalescence. Brittle fracture is a type of fracture that occurs in materials with little to no plastic deformation before failure. The appearance and morphology of brittle fracture can be characterized by several features. Number 1 is smooth and flat fracture surface. Brittle fractures often exhibit smooth, flat surfaces compared to the rough and irregular surfaces associated with ductile fractures. This smoothness is due to the propagation of the crack without significant plastic deformation. Number 2 is cleavage or transgranular fracture. In many metallic materials, brittle fractures can occur through the crystal structure along specific crystallographic planes, known as cleavage. This results in a shiny appearance of the fracture surface. In some materials, such as certain ceramics, fractures can propagate transgranularly through the grains. Number 3 is dimpled appearance. Although generally less prominent in brittle fractures than in ductile fractures, some brittle fractures may display a fine pattern of dimples if there is some localized deformation, often referred to as microvoid coalescence. Number 4 is radial and conical features. The fracture surfaces can sometimes exhibit radial patterns or conical features, especially in brittle materials subjected to tensile stress. This can suggest the direction of crack propagation. Number 5 is fracture origin points. Brittle fractures often start at defect sites, such as voids, inclusions, or stress concentrators. These initiation points may be identifiable on the fracture surface. Number 6 is presence of secondary cracking. In some cases, brittle fractures may exhibit secondary cracks that can be perpendicular to the main fracture surface, often referred to as secondary cleavage cracks. Number 7 is lack of plastic deformation. In brittle fracture, there is little to no visible deformation before the fracture occurs. The lack of necking, which is typical in ductile fracture, is a key characteristic. Number 8 is color and texture variation. The surface may show variations in color and texture due to the material properties, exposure conditions, or environmental factors at the time of fracture. Overall, the morphology of brittle fractures tends to be characterized by distinct features that can be used to identify the nature of the fracture and the conditions under which it occurred. Understanding these characteristics is crucial for material selection, design, and failure analysis in engineering applications. Prevention and/or mitigation. Prevention and mitigation of brittle fracture damage involve a combination of design, material selection, fabrication, and testing measures. Here are some key prevention and mitigation strategies. Number 1 is design. The first of prevention and mitigation strategies in terms of design is to avoid sharp notches and stress concentrators. Design components with smooth curves and rounded corners to reduce stress concentrations. The second of prevention and mitigation strategies in terms of design is to use fail-safe design. Design components to fail in a ductile manner, allowing for some degree of deformation before failure. The third of prevention and mitigation strategies in terms of design is to consider fatigue loading. Design components to withstand repeated loading and unloading cycles, which can lead to fatigue failure. Number 2 is to considering material selection. Such as the following. Choose materials with high toughness, select materials with high fracture toughness, or KIC, and high strain energy release rate, or GIC, to resist brittle fracture. And then to use materials with good ductility. Select materials that can absorb energy and deform plastically before failing. And then to consider material processing. Select materials that have been processed to minimize defects and inclusions, which can act as crack initiators. Number 3 is fabrication. Such as the following. The first to be considered in terms of fabrications is welding and joining. Use proper welding and joining techniques to minimize residual stresses and ensure sound joints. The second of key prevention and mitigation strategies in terms of fabrication to be considered is heat treatment. Apply heat treatment to relieve residual stresses and improve material properties. The third of key prevention and mitigation strategies in terms of fabrication to be considered is surface finish. Ensure a smooth surface finish to reduce stress concentrations. Number 4 is operational measures. The first of key prevention and mitigation strategies to be considered in terms of operational measures is to avoid low temperatures. Operate equipment within a temperature range that minimizes the risk of brittle fracture. The second of key prevention and mitigation strategies to be considered in terms of operational measures is to control pressure and loading. Control pressure and loading conditions to avoid excessive stresses. The third of key prevention and mitigation strategies to be considered in terms of operational measures is to monitor and control corrosion. Monitor and control corrosion to prevent degradation of material properties. Number 5 is other measures. The first of key prevention and mitigation strategies to be considered in terms of other measures is to use fracture mechanics analysis. Use fracture mechanics analysis to predict the likelihood of brittle fracture and identify potential failure modes. The second of key prevention and mitigation strategies to be considered in terms of other measures is to implement a fracture control plan. Develop and implement a fracture control plan to ensure that components are designed, fabricated, and operated to minimize the risk of brittle fracture. The third of key prevention and mitigation strategies to be considered in terms of other measures is to provide training and awareness. Provide training and awareness to personnel on the risks of brittle fracture and the measures to prevent or mitigate it. By implementing these measures, the risk of brittle fracture damage can be minimized, and the integrity of components and structures can be ensured. Inspection and monitoring for brittle fracture damage mechanisms based on API 571. The first is inspection is not normally used to mitigate brittle fracture, and the second is susceptible vessels should be inspected for pre-existing flaws/defects. Several inspection and monitoring methods can be employed to identify signs of brittle fracture damage. Number 1 is visual inspection. Surface examination. Visual inspections can reveal cracks, surface irregularities, or anomalies on the material surface. This can often be done with the naked eye or with the aid of magnifying tools. Number 2 is non-destructive testing, or NDT. In this case, NDT could be divided by 5 categories as the following. The first is ultrasonic testing, or UT. Ultrasonic waves are used to detect internal flaws, cracks, and discontinuities. It is effective for detecting subsurface and near-surface defects. The second of NDT method is magnetic particle testing, or MT. This method is used for ferromagnetic materials to detect surface and near-surface flaws. A magnetic field is applied, and fine magnetic particles are used to reveal cracks. The third of NDT method is dye penetrant testing, or PT. A liquid dye is applied to the surface of non-porous materials, and after a certain period, excess dye is removed. A developer is then applied, revealing any cracks by the dye that penetrates them. The fourth of NDT method is radiographic testing, or RT X-rays or gamma rays penetrate the material and create an image on a film or digital detector. This method can detect internal cracks and voids. The fifth of NDT method is eddy current testing. This technique utilizes electromagnetic induction to detect surface and near-surface defects in conductive materials. Number 3 is acoustic emission testing, or AET. This method involves monitoring high-frequency sound waves generated by the rapid release of energy from crack propagation. It is effective for real-time monitoring and detection of crack development. Number 4 is thermal imaging. Infrared thermography can be used to detect differences in temperature on the surface of a material, which can indicate areas where cracks or other defects may exist. Number 5 is strain gauges. Monitoring strain in materials can provide insights into the stress levels that may lead to brittle fracture. A sudden change in strain patterns could indicate imminent fracture risks. Number 6 is finite element analysis, or FEA. While not an inspection method per se, simulation and modeling can help predict where brittle fractures might occur based on stress concentrations and fatigue analysis. Number 7 is fractography. In the event of a failure, examining the fracture surface using techniques like scanning electron microscopy, SEM, can provide valuable information about the nature and causes of brittle fracture. Number 8 is critical thickness measurement. For some materials, measuring the thickness and comparing it to established critical thickness criteria can reveal susceptibility to brittle fracture. Number 9 is condition monitoring systems. Automated or semi-automated systems can continuously monitor structural health using a combination of the above methods and algorithms to predict potential brittle fracture risks. Combining several of these methods is often the most effective way to detect brittle fracture damage. Regular inspections, advanced NDT techniques, and continuous monitoring can help ensure that materials remain safe and functional throughout their life cycle. Regular inspection and maintenance. Regularly inspect components for signs of damage or degradation, and perform maintenance tasks, such as replacing worn or damaged components. Thank you.